Remember when craftsmen shaped metal with nothing but a hammer and anvil? Well, we've come a long way, folks. Today, we're looking at something that would have seemed like pure magic to our grandfathers, the Repcon hot spinning lathe. Hot spinning is a fascinating dance between heat and precision. Picture this: a solid metal blank, mounted securely on a powerful lathe, begins to rotate. But here's where it gets interesting. As that workpiece spins, specialized torches direct intense, concentrated heat onto specific zones of the metal, raising temperatures to the point where steel becomes surprisingly pliable. The Repcon system is the Cadillac of hot spinning equipment. It combines old-world metalworking principles with computer-controlled accuracy. As the metal glows cherry red from the applied heat, a hardened steel roller, guided by programmable controls, presses firmly against the softened surface. The spinning motion, combined with that steady pressure, gradually forms the metal into complex shapes like rocket nose cones, pressure vessel heads, or large diameter pipes. What makes this process remarkable is the transformation. That rigid piece of steel, which would normally require massive stamping presses or forging hammers, flows almost like clay under the roller's touch. The Repcon's precision controls ensure uniform wall thickness throughout, something that was nearly impossible in the old days. Let's talk about something you've probably turned 1,000 times without giving it much thought: those brass knobs on your gas fireplace or stove. These little beauties are precision-engineered components, and watching them being made is absolutely mesmerizing. The process starts with brass rod stock, an alloy that's been a craftsman's friend for over 2 centuries. Brass, that warm, golden mixture of copper and zinc, machines beautifully and resists corrosion, which is exactly what you want when dealing with gas appliances. The CNC lathe grips the brass rod firmly in its chuck and begins spinning at precisely calculated speeds. Now, here's where modern technology shines. Unlike the manual lathes your dad or granddad might have operated, where every cut required a skilled hand on the controls, this CNC machine follows a computer program written by expert machinists. Watch as the carbide cutting tool approaches the spinning brass. It begins carving away material in a carefully choreographed sequence. First, it faces off the end, creating a perfectly flat surface. Then, it turns the outer diameter, bringing the brass down to exact specifications. We're talking tolerances within a few thousandths of an inch. Next comes the decorative knurling or fluting that gives your fingers grip. The machine indexes to precise positions, cutting those familiar patterns that are both functional and attractive. Then it bores out the center hole where the valve stem fits, followed by any threading operations. The beauty of CNC is consistency. Every single knob comes off that lathe identical to the last one, meeting the same exacting standards. Now, here's something that would have amazed the old-timers at the copper mills: the upcast continuous casting system. If you've ever worked with copper plumbing or refrigeration, you know thin-walled copper tubing is the lifeblood of modern HVAC and plumbing systems. But how it's made today is nothing short of revolutionary. Traditional copper tube manufacturing used to be a multi-step headache. You'd cast copper into billets, reheat them, pierce them, draw them down through multiple dies, and anneal them repeatedly. The upcast system turned that whole process on its head, literally. Here's the genius of it. Instead of pouring molten copper downward like we've done for thousands of years, upcast draws it upward. Molten copper, heated to about 2,000 degrees Fahrenheit, sits in a holding furnace. A water-cooled mold with a graphite die descends into that molten bath, and as it slowly withdraws upward, the copper solidifies around a mandrel, forming a continuous tube. Watch that glowing copper emerge from the casting wheel. It's being drawn upward at a steady rate, while water cooling rapidly solidifies the outer wall. The result? Seamless, thin-walled copper tubing with remarkably uniform properties, produced in one continuous operation. Those massive coils you're seeing can be thousands of feet long. What makes the upcast system particularly brilliant, and this is something engineers really appreciate, is its flexibility and efficiency. This cost-effective, environmentally friendly production line is also available as a hybrid solution, which is perfect for optimizing production capacity between copper rod casting and copper tube manufacturing. That means manufacturers can switch between different products without massive retooling. The system's environmental benefits are substantial too. Less energy consumption, reduced material waste, and minimal emissions compared to traditional methods. Back in the day, copper mills were hot, dangerous places with tremendous energy requirements. This modern approach produces superior tubing while being gentler on both the workforce and the environment. If you told someone 50 years ago that we'd be building machines with blades longer than a football field to harvest wind energy, they might have thought you'd lost your marbles. But here we are, watching the assembly of an Enercon wind turbine, and folks, this is engineering on a cathedral building scale. Enercon, a German manufacturer, has been perfecting wind turbine design since the 1980s. These aren't your grandfather's windmills. We're talking about machines that stand over 600 feet tall, generating enough electricity to power hundreds of homes. The assembly process is a marvel of logistics and precision. It starts with the tower sections, massive steel cylinders, each one carefully fabricated and coated to withstand decades of weather. These sections arrive on special transport trucks and are lifted by enormous cranes, one atop another, bolted together with hundreds of high-strength fasteners torqued to exact specifications. Next comes the nacelle. That's the house-sized generator unit at the top. Inside that aerodynamic shell sits Enercon's revolutionary direct-drive generator. Unlike conventional turbines that use gearboxes, which wear out and require maintenance, Enercon's design connects the rotor directly to a ring generator with thousands of magnetic poles. It's more reliable and requires less maintenance, crucial when your equipment is 400 feet in the air. Watch as the crane carefully positions the nacelle atop the tower. The alignment must be perfect. We're talking millimeter precision on a component weighing over 100 tons. Technicians secure it while others connect electrical systems and control cables. Then come the blades, each one an aerospace-quality composite structure stretching over 200 feet. These aren't just bolted on randomly. Each blade is individually weighed and balanced, then installed at precisely calculated angles. The pitch control systems that adjust blade angles are installed and calibrated. These systems allow the turbine to optimize performance in varying wind conditions, automatically feathering the blades in high winds to prevent damage. Finally, the hub nose cone is fitted, giving the turbine its distinctive appearance. After extensive electrical testing and computer systems calibration, this giant is ready to begin its 20 to 25-year career generating clean electricity. Now let's look at something that really showcases industrial muscle: bending thick steel plate. This is 200 millimeters thick. That's nearly 8 inches of solid steel. Bending something like that used to require massive trip hammers and lots of heat. Today, we do it cold with hydraulic power and computer precision. Here's how this beast operates. The steel plate, weighing several tons, is positioned on the machine bed. The bottom rollers are fixed in position, while the top roller, driven by powerful hydraulic cylinders generating hundreds of tons of force, can be raised or lowered with incredible precision. The CNC control system programs automatic sequences for the bending steps, calculating exactly how much pressure to apply and at what positions. Watch as the plate begins moving through the rollers. The top roller applies steady, controlled pressure, gradually forming the steel into a curve. The beauty of the CNC system is consistency. It calculates spring back, that tendency of steel to partially return to its original shape, adjusts for material thickness variations, and ensures the finished curve meets exact specifications.